We are live. Maybe. So the streaming setup today is different from what it usually is because I am streaming from Linux, so any number of things might go wrong. With that in mind, can somebody write in chat confirming, hopefully, that audio works, video works, stream works, etc. I will leave this up for now and we will start in a couple minutes. Oh, I need to get my tea. Okay, that is good, thank you. We should probably, yes, I'll spend a couple minutes talking about the agenda. Oh, hold on, let me. Where is this here? All right, whatever. Let's just keep it like this. So, the stream today is gonna be working on triangle culling for the Vulkan renderer that has been occasionally developed on stream. Before we go into this, let's just spend a moment. So this project is usually developed on stream. If you look at the commits, then we last did a stream on this on July 16th, so like 6 months ago. Since then, in September, I spent a little bit of time working on this project off stream. So the reason why I didn't stream this work was A, it was a little bit like sort of technical and boring, but B, it was done from Linux using the Vulkan mesh shader extension that was sort of in development. I expected GPU hangs. I did hang my system a few times while doing this, and since I don't have a separate streaming setup, I wasn't really comfortable sort of streaming that work. But so I want to spend a couple minutes talking about what has happened sort of behind the scenes, and really the only thing that happened is, or the big thing that happened is we changed the project from using the NVIDIA specific mesh shader extension to the VKXT mesh shader. The reason why this is important is that right now I'm streaming this from an AMD GPU, not an NVIDIA GPU. And for the longest time, this project worked on non-NVIDIA GPUs, but didn't actually use mesh shaders on non-NVIDIA GPUs, which was unfortunate because one of the purposes of this project is to experiment with mesh shading. So fortunately, there was an extension released by Kronos in September, I think, or maybe late August. And this extension was very quickly supported in an open source AMT driver called RADV. The support was experimental, In fact, a couple days ago, the most recent RAD driver, I don't know at what point the extension gets official or not, but like it seems like now there is actual official supported RAD driver for this. The caveat is that I think for the official support to work, you have to be on the latest Linux kernel, which we are not. But we are gonna be, I have a version of RAD compiled from source where we can actually use mesh shader on the MD hardware that I have, which is nice. So really this required a lot of small changes sort of here and there because the specifics of the extension are different, but the fundamentals of the extension are like the computational model of the extension is the same. So if you want a refresher on this, you'll have to go back to whatever stream was it when we actually implemented support for the video mesh shaders. But today we are going to be looking a little bit at culling, and for people who know all of the ins and outs of AMD GPU, some of the things might be unsurprising, but for people who don't, some of the things might be surprising, even if you don't particularly care about mesh shaders. So that's kind of what happened off stream. The other thing that happened off stream is we updated the mesh optimizer library, which we use to generate meshlet data and optimize meshes to the latest version, which is nice because the latest version has it generates more efficient output for meshlet data, so we get a little bit more efficiency that way. I have two AMD drivers installed on my system. Ordinarily, I would have liked to maybe like run on both or use the AMD developed driver, but only one of these drivers supports mesh shader extensions, and the version that I have compiled requires me to let me increase the text a little bit. Don't think we'll need the terminal output much. So the way we can run our application using the using the mesh shader extension is a little, so we have to use the version of the driver that I have built locally, which is just a Mesa open source project build. And we have to enable mesh shaders. Again, if you use latest Mesa and latest Linux kernel, I don't think you need to, but for us, we do need to. And we'll talk about what this is in a little bit. So let's recap where we are at. And also check that the stream actually works with the graphics code running, which I haven't checked before. So we have this code. We have a series of culling sort of algorithms implemented. If I open it to the entire screen, we'll see that we are currently running with mesh shading on. This is on an AMD GPU. And we can also toggle between mesh shading being on and off, which is nice. We can also see, so there's a triangle count display here. And we can see that with mesh shading on, we have 74 million triangles, give or take. And with it off, we have 84. The reason for this is that we have, on prior streams, we've implemented some meshlet culling approaches. And this is kind of what we are going to expand on today. All right, so let's double check that the stream didn't die and things. Okay, cool. So, what is the problem that we are solving today? Well, let's look at the culling code. Oh, this is the wrong project. This is the right project. So let's look at what kind of optimizations we do today in terms of sort of scene rendering. So one of them is when we render meshes, we do frustum culling for meshes, very basic, and we do occlusion culling for meshes. And again, if you are curious about how this works, refer to prior stream. It's a really cool occlusion culling technique that doesn't have sort of frame lag or CPU-GPU syncs. That's done entirely on the GPU, and it's more or less free. We pay like a little bit of the cost for having to do this, but it's like very, very small. So that's cool. From the mesh culling perspective, we are pretty solid. Like, it's hard to imagine a lot more that we could do here. And we also do level of detail selection on the GPU. However, what happens after this is we render the mesh, and when we use traditional rasterization pipeline, we just render the mesh using vertex shaders and fragment shaders. When we use the meshlet-based shading pipeline, then we have this thing which we implemented at some point, which is we do what's called cone culling. So cone culling takes where is my, okay. So cone culling takes the entire cluster. Wait, sorry, I'll have to get used to this a little bit. I'm used to using the desktop application for Microsoft Whiteboard, but this is a browser application. How do I drag this thing? Can I even drag this thing? Okay, this is how I drag this thing. Oh, okay. How did the phrase cone cull appear here? What? Okay, let's not question what is happening on screen. So we work with meshlets, and meshlets are a small set of triangles. We use up to, I think, 128 triangles per meshlet right now. We are going to ignore some of the hardware efficiency details of how we work with meshlets today, because this is going to be a subject for either a later stream or some later post, or I don't know yet how exactly we'll explore this. But so today we split the mesh into meshlets. Meshlet is a small number of triangles. When you render a mesh, the GPU does backface culling for you. So it takes triangles that are facing the other way from the camera and doesn't render them. What we do today is, so there's this realization, oh right, and in any mesh, in any closed mesh, you would typically expect around half of the triangles looking towards the camera and around half of the triangles looking away from the camera. So in theory, backface culling should reduce the number of triangles that you have to feed to the GPU by half, or into. What we do today is we look at a meshlet. So this is like a bunch of triangles, right? And each triangle has a normal, or it's a face normal, not right. Yeah, each triangle has normal. So then we look at, we build up some data ahead of time that says where should the camera be for all triangles in a given meshlet to have the triangle facing away from the camera. And at runtime, we say, well, if the camera is in this region, which is a cone, then we don't need to render any of the triangles. So that is cool in theory, right? Essentially, instead of doing this backface culling test per triangle, we do this on the entire meshlet and then just don't render the entire meshlet. So unfortunately, the efficiency of this is not as good as we would hope. So again, the optimal backface culling efficiency is you reduce the number of triangles by half. So let's just say we are going to work with the smaller view so that I don't have to do like full screen and stuff. In the smaller view right now, the mesh shading path renders 74 million triangles and the non-mesh shading path renders 84. So that's not half, right? That's what, like a little bit more than 10%. Why does this happen? So first, so we have, it's going to be a little bit confusing because I have various indicators of kind of toggles enabled for various features that are all in this title bar, and the title bar is really long now, so you can't see anything. But it's going to be reasonably, so I'm going to disable level of detail right now. So right now we use level of detail when rendering all of this mesh data. Let me disable it. So now we render 400 million triangles, which is a lot, with mesh shading enabled. And with it disabled, we render 572. All right, let me close this. So 400 over 572. Okay. So lesson learned: don't use BC to do math. Use Python to do math. So when we disable level of detail, we render around 70% of the triangles that we have in our scene. Was it 70? Damn it, 75 by 84, I think. I forgot. Let's say it was 75 by 84, maybe it was 72 by 84, whatever. So when we have a level of detail enabled, we actually only cull around 10% for triangles. So our culling efficiency of backface culling is not great in general, like it's 30%, whereas we would expect 50% naively. And when we enable LEDs, it's only 10%. What is going on? Why is it this bad? So the reason is that when you look at complex geometry, let's look at a side view of a set of triangles. So if you're very lucky, then your meshlet looks like this. And we basically create a cone that looks kind of like this, and so whenever the camera is here, then we don't render the meshlet. And you can see that this sort of half space it's less than half of the entire plane, but it's like reasonably close. I don't know what it is, 40%, 45%, so it's like reasonably good, right? You would expect reasonably good culling probability from having the camera be in that region versus not be. However, what often happens in practice on real geometry is you see things that are more complicated. For example, maybe your meshlet is like this. Maybe this is your triangle structure, right? And we have a lot of triangles, we have reasonable detalization in geometry, so you could expect to see this sort of this arrangement of geometry. What happens here is really problematic, because even if the camera is here, and you would normally say, oh, hey, you don't actually see this geometry. Well, in fact, you do, because when the camera is here, we do render, well, we have to rasterize these faces, because they are front-facing from the camera perspective. And so when you look at the entire meshlet, some of the faces are front-facing, some of the faces are back-facing, and we can't cull the whole thing. So that is a problem. Now, there is ways to like improve a little bit the culling data for this, for things to be more efficient. I looked at some of them. I have so far been disappointed with results. So let's just assume this is kind of what the problem is. So that is unfortunate. The other problem that we have is that we render a lot of small triangles because in general our triangle density is very, very high. And so a lot of the triangles that we have, they actually don't result in pixels on screen because they are smaller than the pixel, so to speak. And we feed all of this data into the GPU. But this is a separate point. So what happens when you enable level of detail is that you reduce the number of triangles in a lot of the meshes that you render. By virtue of this, you increase the probability, sort of, that something like this would happen, because you take a lot of sort of planar regions that were represented by a lot of triangles, and you're simplifying them to just a few triangles. And so your meshlets, which are like 120 triangles in size, they start to aggregate more and more features from around the mesh, which increases the chances of us hitting this problem, right? So this is why when we enable level of detail, our backface culling implementation, it like works. It's better to have it than to not have it, because it still saves you 10% of triangles, but you know, it's not ideal. So I'm trying to figure out, there's two things I want to talk about before we actually start writing code, and I'm not sure which one should be first. Let's start with this one, because I think this predates. Let's actually not start with this one. Let's start with something else. So, so this is a problem, right? We render a lot of triangles. We'd like to render fewer triangles. There's something interesting that happens on AMD GPUs though. So I have all of these crazy flags that I pass in right now. Let's remove one of them. And in fact, the same thing would happen if you run the code on top of the other AMD driver that I have installed. So let's first run again to note the baseline. So we are rendering 74.4 million triangles. Cool. Is it a lot or is it not a lot? Let's remove this debug flag and render again. And disable mesh shading. Right, we rendered 87 actually, or without mesh shading, whatever the number is. So this thing is oscillating, but basically without mesh shading, without weird flags passed in, the triangle counter statistic from the GPU tells us we're rendering only 7 million triangles. when we have mesh shading disabled. When we have mesh shading enabled, we render 74. So as a probably predictable consequence, when mesh shading is enabled, we are actually much slower on an AMD GPU when we have mesh shading disabled, because somehow when you disable mesh shading, a lot of the triangles are just not getting rendered. How can this be? Well, the thing is, and I'm going to now use this presentation a little bit for, this is work that Graham Wildell did in 2016. You should read the slides offline. They're good. We are going to be basically implementing some of the similar techniques mentioned here today, but in a different context, like the hardware specifics are very different because this is pre-mesh shaders. Here's what this presentation is basically saying. It is saying that on an AMD GPU, there is 4 geometry engines, and each engine can cull 1 triangle per cycle. I don't know which AMD GPU this is, but on the same AMD GPU, for the same geometry, for each geometry engine, there's like a shader array that can do 8,000 scalar arithmetic operations per cycle. 8,000, I think, is the peak performance, as in it's treating, is basically saying if every operation is a multiply add, it's 2 operations, 2 primitive operations per cycle, etc. So this is like the worst case, but so essentially, while the fixed function unit that calls geometry or that renders triangles, I think in this case the one that calls triangles. So there is a hardware unit that also can do backface culling and probably triangle rejection for triangles that are too small. So it can do 4 triangles per cycle. We can do 8,000 ALU ops in the same amount of time. So actually the whole GPU has a lot of computational power per triangle. But if you render a lot of geometry, you are likely to be bottlenecked in the small fixed function unit that just can't keep up. And so it can be more efficient to spend some of these computational resources that you have on the GPU, removing the geometry that you wouldn't have rendered otherwise, to get better efficiency. So there is a sort of more recent developments that also Graham Wildell was involved in is Nanite from Epic. Nanite has some of the same foundational questions in its implementation. Like, it's also asking the question, well, if we have so much geometry, can we stop using some of the GPU's fixed function rasterization units to sort of render it efficiently? But we will not talk about this. So these are slides from 2016. I believe they talk about, I guess one of these is a PS4. So the middle one is the PS4. The bottom one, I think, is the whatever was the recent GPU from AMD at the time. So I also have here, this is 5700 XT actually. So you can look at the up-to-date data for, there is this question essentially, how many triangles can a GPU call in a fixed function unit versus how much computational power you have. You can look up these numbers for more recent ones. I just realized this is the RDNA 1 probably. So I'm using 6700 XT right now, and this is talking about 5700 XT. So I have one generation up of a GPU from this white paper, but this talks about something similar. It says here, I don't remember where it is. Let's see. Maybe this was not from here. I guess it was this Reddit post that I found that says that, and I don't know, I'm sure this is true information that can be validated, but essentially RDNA 2, which is the GPU that I have, can rasterize 1 triangle per clock and cull 2 triangles per clock. So it has double culling rate from what we would, from essentially for however many geometry engines it has double culling rate from this. but it's still small number, right? I don't know how many geometry engines this GPU that I'm using has. This one that I had here had 2. So overall, these are like small numbers, right? There is way more LU capacity than we have triangle culling capacity. So this says that it might be actually efficient for us to do some of the per triangle culling work on the GPU ourselves. And in fact, this is exactly what the driver does. So when we don't use mesh shaders under an AMD driver that runs on RDNA hardware, I don't know if all AMD drivers do this, because there's somewhere between, I think, 3 and maybe 4 AMD drivers across like Linux and Windows and different drivers and stuff like this. So I don't know if all AMD drivers do this, but certainly a lot of them do. We can run our code on the mainline driver, or the official AMD open source driver, which is AMD VLK, which is different. And so this says 6.8 million triangles, and there I think we had 6.7 on Radov. So all of these reduce the number of triangles by doing some amount of culling that happens on the GPU. So all of this is automatic. It applies when you have vertex and fragment shaders. Radov only does this when you use vertex and fragment shaders, and does not do this when we use mesh shaders. And so to be able to catch up with what the traditional rasterization pipeline with this driver magic is doing, to be able to catch up to this in terms of performance, we'll have to re-implement some of this ourselves. So when you pass this non-GGC flag, this magic in the driver is disabled. And so in this scenario, we can win versus traditional rasterization pipeline, right? So this is kind of the general idea, right? The hardware, my understanding of the hardware mechanism that the driver uses behind the scenes is that, so AMD has this thing called primitive shaders, which mesh shaders I think are implemented on top of, and I won't talk about primitive shaders because I don't actually know all of the details, but it's not quite a mesh shaders. There's some difference in sort of execution semantics, and we'll have to talk about this more in future streams if we explore the sort of hardware efficiency considerations of mesh shading on different vendors. But what the shader can do is it can reference essentially triangles that are going through the rasterization pipeline. It can load the data, load the vertex data for these triangles, and then perform a set of culling operations, and then output or not output the triangle to the rasterizer. And so this can be done behind the scenes in driver. So when we use the mesh shader, we'll have to do it ourselves. Let's look at the traditional culling pipeline that you would do in cases like this. And then we will, so this talks about the cluster culling also, which we do. The one thing I should note, which we don't do, is we don't do per cluster occlusion culling, which would be nice, but it's like infrastructurally difficult to do. So we might do this at some point, but we aren't doing this right now. Oh my God, where is this? Okay, yes, this is what I'm looking at. This is what I wanted. Yeah, this was announced on Mastodon. And yes, it would be perfectly reasonable to not expect a new stream because we had like a half a year break, and before that we had another maybe multi-year break. So this is not a very regular series at this point, but essentially it's a useful vehicle for me working with working through some of these problems, and I might as well stream this. So let's look at Graham's presentation, and let's look at this culling sequence, and we'll talk about sort of how this may map towards what we can do, because our situation is a little bit different. So can I let me try to, you would normally not think of asking the question, can I copy and paste this? But This is Linux, so God knows what happens here. Okay. All right. So here's the culling sequence that paper uses. Let's look at this. So unpack index and vertex data is just like the technical thing that you'll have to do to be able to do this work. We already have this in our mesh shaders. Orientation and zero-error culling. So this is basically backface culling. The reason why this mentions zero-error culling is that when you do backface culling on the GPU, or not on the GPU, like during rendering triangles, you have to essentially look at the signed area of the triangle sort of from the perspective of the camera. And when the signed area is negative, the triangle is backfacing, but when the signed area is 0, the triangle is just empty, like 0 area, so you don't have to render it. So this is 0 area is free if you already do orientation culling. So then it does perspective divide, which is an interesting order. Normally you would flip them. You would first do perspective divide and then you would evaluate orientation. This work does it for a reason in this order. For us, the considerations are a little bit different. I'll talk a little bit about this. So then it does depth culling. So this is occlusion culling. We do occlusion culling on a per mesh basis. We could do per mesh occlusion culling on a per cluster basis. We don't do this right now. We don't really care about doing this on a per triangle basis is my claim. My claim is we don't really have a problem with, well, so whenever you look at any of these culling steps, so depth culling, then it does small primitive culling, which is essentially if the triangle is smaller than the pixel, or rather if the triangle doesn't result in any pixels generated. This is slightly different. So it does frustum culling, and then the rest is just sort of operational. So really it does 1, 2, 3, 4. It does 4 culling steps, and then perspective divide and everything else is like a prerequisite to be able to do some of these steps. So in theory, you can do all of these on a per triangle basis without doing anything on a per mesh basis or per mesh LED basis, right? And you would end up with the same result. But when you have this hierarchical structure, so we have a hierarchical structure where we have mesh, and then we have meshes that consists of meshlets, and then we have meshlets that consist of triangles. We can choose which granularity we do any culling step at. Sometimes we may choose to do a culling step at multiple granularities. And this choice, for example, if we decide to not do something on a per triangle level, but to do something on a per meshlet level instead, what we are doing is we are reducing the amount of work that needs to happen to make this culling work. But we are reducing the efficiency because there's going to be some cases like we just talked about the backface culling where we do the culling at the higher level of granularity with less efficiency, and so we end up with more triangles that we have to render. But more triangles doesn't always mean that it's worse, especially on different kinds of GPUs. It's hard to know, so I don't have an NVIDIA GPU, so we aren't going to be able right now, so we aren't going to be able to test anything that we do today from the performance perspective on an NVIDIA GPU, but maybe the considerations that are different in terms of which kind of, how much LU is it worth it for you to reduce the number of triangles by like 5%, by an extra 5%. The other thing is, so this triangle culling unit that is fixed function can do like ostensibly 8 per cycle or whatever. This is not a shared resource, as in it is used by the geometry rendering, by the rasterization, and that's it. LUs are a shared resource. You may be doing a bunch of other stuff at the same time as you're rendering geometry with LUs. They run vertex shading, obviously, they may run fragment shading, you may have asynchronous compute for some other stuff in your scene. So while it is true that we can be more efficient in terms of LU than we are in terms of fixed function hardware, or we have more LU resources than we have fixed function hardware resources here, we can't say, oh, this means we have 100x LU or 1,000 XLU or whatever, this must mean we can use that entire sort of set of resources to do culling. Well, if we do this, then we will not be able to do any useful work, right? So there's some balance between these two, and it's hard to evaluate this balance. So today we do, let's just use these numbers that I have there for reference. So right now we do 1 on the meshlet level, we do 2 on the mesh level, we do 4 on the mesh level, and we don't do 3. So where I want to get to today is we will not touch the mesh level. The mesh level is a little bit difficult to touch. You can do small primitive culling on the mesh level, but it's not, for our scene, it's not very impactful. So it's sort of more work than it's worth. More work, not computationally, but like it's more time for me to write code than it's worth right now. I want to add 4 to the meshlets, because on the triangle level, I want to do 1 and 3 today. So Graham's work does 1, 2, 3, and 4 on the triangle level, and then presumably whatever Frostbite does. Graham's work also does something on the cluster level, maybe just 1, or maybe also Frostum. So Graham's work does a bunch of stuff at a bunch of different levels. From the triangle level, again, I want to do like the minimum amount of work computationally and on stream possible to be reasonable. We can do Frostum culling on a per triangle level. It is not hard. However, my suspicion is this. So for every one of these optimizations that you kind of lower at the next level, you're doing this for a reason. You're doing this because it saves you a lot of geometry that you would have to otherwise sort of rasterize. And I want to do these to the extent that it substantially reduces the amount of geometry that we need to render. So I know backface culling is a problem. We just, on the triangle level, we just discussed that today our culling efficiency when we have LODs enabled, which is the pragmatic configuration, is 10%. So we know that we can almost halve the number of triangles that we rasterize by doing backface culling ourselves. And we know, or I know, it's certain that we have a lot of triangles that are subpixel, that don't contribute to the number of pixels to rasterize. We rendered something like 80 million triangles. Even if you cut it by half from backface culling, it's 40 million. The window resolution that we had maybe 1 million pixels or something. Like, it's clear that we have a lot of triangles that are subpixel. But Frostum culling may not be a big issue. The reason why Frostum culling may not be a big issue on the triangle level is that when you do this on the meshlet level, then the extra triangles that you still render that would fail the Frostum culling check, they are slightly outside the border of the screen, right? So you would have the screen and you would have a meshlet that's like this, and there's a triangle that's here. And so you rasterize this triangle. But comparatively, there's way more meshlets, probably, I'm guessing, that are sort of, that don't have this property, that are actually passing the Frostum check and are on the screen. And so yes, we would save some amount of triangles if we do this. But is the balance worth it? Who knows? So I'm not going to be doing this. For what's it's worth, I don't know what the official MD driver does because I haven't looked. But the Radov driver does do 1, 3, and 4 on the per triangle level. So we are not going to be doing 4 on the triangle level, even though the MD driver does do that. And this is the flexibility that we get from mesh shaders. So we can say, we think given our scene characteristics, it's just not worth it to do everything at triangle granularity because we have this meshlet structure that can carry some of the load. And the final thing I will note before we start writing code is this. So when the driver does this, and also when in Graham's work, you don't have, I guess in Graham's work, you do have the cluster structure. So I don't know exactly how that works. I haven't reviewed the entire slide deck. I read it like many years ago, and I've just briefly glanced at it now. But what the driver does is it takes every triangle in isolation and then works on a triangle in isolation. So a triangle, for example, has 3 vertices. And I'm pretty sure Graham's work does the same thing, yeah. So the triangle has 3 vertices. And so to be able to, for example, do small primitive culling, you have to project all of these 3 vertices to the ellipse space. So you have to do the perspective divide. So you have to do this division for 3 vertices. In fact, this is why if you look at this sequence in Graham's work, it does orientation before perspective divide, because you would expect to cull half of the triangles away with this. And this means you can skip perspective divide for half of the triangle. So that's cool. However, when you have the meshlet structure, then you have, on average, we have something like 64 vertices, and let's just call it 90 triangles. I don't remember what the number is in practice. 90 triangles is 270 sort of triangle vertices. If we can do something on a per vertex level before we do the culling, we can do that, and if we do this, we might save more work compared to the case where we don't have this meshlet structure, right? This is the luxury that we have that the driver doesn't have, and whatever Graham was doing, I think, doesn't do. Because we have these meshlets that we know have a small number of shared vertices and a number of triangles. So for what we can do is we can do perspective divide for every vertex in the meshlet, because odds are every vertex in the meshlet is probably going to participate in a triangle that is not back-facing. It's not quite guaranteed and it's not quite true, but it's probably better to do this work per vertex because you have a guaranteed sort of workload of 64 versus doing this on a per triangle vertex level where you have 270 triangle vertices. Let's say you cull away half the triangles, so end up with 135 triangle vertices that you have to process. This is still twice as big as the number of vertices, the number of shared vertices in the meshlet. So hopefully that makes sense. I'm not like explaining this to I'm not giving a too detailed explanation of this because I want to start writing code, but the motivation essentially for some of what we are going to do in how it's different from what this presentation did and what the driver does is we have meshlets, so we might as well use some of the characteristics of meshlets. All right, so that's kind of it. So now we're going to write code. So the hope today is that we are going to do all of these 3 things. So frustum culling for meshlets, which is not going to be a huge deal, I don't think, because we already do frustum culling for meshes, but might as well. But then the important thing is the per triangle work. And we're probably going to start with per triangle work, and then we will see sort of if we have time left and stuff. One final note, I'm going to breeze through some of this. I'm not going to explain this I'm not going to explain the math after this segment, but so when you do perspective divide, there's a question as to what happens. So perspective projection has a singularity on the plane that contains the camera position, where W is 0. And dividing by 0, you can do this, but it doesn't end very well. So there is this general question as to what do you do with triangles that cross this singularity plane. What we are going to do with this is we are going to just ignore them, because for us we don't actually care about doing the perfect job at culling, because the rasterizer will do the correct thing. So whatever we do has to be sort of, we know for a fact rasterizer will not generate any pixels for this, so we might as well drop this, but we don't have to be thorough. We don't have to eliminate every single triangle that the rasterizer would not otherwise sort of render, right? So because of this, we are going to try to do a version of this that doesn't really care about sort of crossing the perspective plane and stuff like this, because we can just ignore some of these triangles. All right, so that's kind of it for the introduction. This was a long introduction, but now we're going to actually start writing code. So the first thing, let me see if I have everything. So I have this command line. So our goal is to get, let me remove, we don't really need this non-GGC thing anymore. So our goal is to get from 74 million triangles or thereabouts to around 7. I don't know how far we will actually be able to get today. Let's go. So the first thing we need to do is to be able to do per triangle culling. Actually, right. So to be able to do per triangle culling, we need to have the projection matrix, which we do have here. So for this, we don't need additional data. So I guess we might as well just do that. Why do I not have syntax highlighting, by the way? Interesting. Is it smart to install syntax highlighting package on stream? Let's see. This probably, right? Okay. Okay, now we have syntax highlighting. Cool, cool. So as I mentioned, our strategy is gonna be, we are gonna do some of the work on a, so what we need to do is we need to do backface culling first. To do backface culling, if you look at Graham's presentation, because he does it before perspective culling, he uses this cool triangle culling method that doesn't require perspective divide. But what it does require is it requires computing the 3D determinant, the 3x3 matrix determinant in like the perspective space. We could do this like this, but I haven't, ideally we would do both ways and we'll compare. But for now, since we know we are gonna need to do perspective divide, and since to do perspective divide it's more efficient for us to do it per vertex, we'll have to kind of do this for every vertex anyway. There's not a very good way of skipping vertices that belong to no triangles that are being rasterized and do it very, very cheaply in the mesh shader, I don't think. So we're not going to do that. So we're going to just do the perspective divide and then do the 2D sort of 2D signed area thing, and that's going to be fine. Oh, the one thing I didn't talk about is how we're going to cull triangles. So when we have mesh shader extension, that's, I don't think the NVIDIA's version had this. I don't remember. Maybe it did. The Kronos version has this thing called cull primitive ext, which is essentially for every triangle that you output, you can set this extra boolean that says, presumably, do you wanna discard the triangle? So let's set this to true first and foremost. And then I guess we can just set it here. This thing, right? All right, so when you set it to true, everything is culled, so nothing is rendered, which is cool. When you set it to false, everything is rendered. Okay. Oh. So now our job is to compute this boolean right in a somewhat intelligent manner. So we conveniently have triangle indices here because we need to output them. So I should have implemented live shader reload for this like a while back, but I haven't, so we're just gonna power through without it. All right. So the first thing that we need is we need to take every vertex and we need to do the perspective divide. The question is, where do we store? And then from this loop, we have to refer to this data. The question is, where do we store this? So the answer is we need to use shared memory for this. Because the meshlet processes sort of all vertices and all primitives in parallel. I should mention, why does this, oh, this did not reload after the extension, yeah, okay. So I'm not, I don't remember off the top of my head a lot of GLSL syntax, but so presumably this is just shared, okay. So what we are gonna do then, so we need an index. Oh, so we need an entry for every vertex that can be in the meshlet. So we need an array of 64 sort of vertex, transformed vertex structures. We don't have this in a macro, which is unfortunate, but interesting. Huh. All right. For now, we'll just hard code everything. So we are going to take every vertex. So we are going to do backface culling, and we are going to do small primitive culling. We are not going to do frustum culling on a triangle level. So because of this, when we transform every vertex of every triangle, we actually don't need the z coordinate. It's kind of redundant. We will need the w coordinate. So like ordinarily, you would just say, you know, vertex clip or something like this, and you would just say then for every vertex, if culling is enabled, we take vertex clip and we compute it by taking the position. All right, let's do this. Okay. So we've already transformed every vertex to clip to, not quite, we've transformed it to like homogeneous space, but we haven't done the perspective divide. So theoretically, we can just do clip xy, clip w, right? And in theory, we are done. The reason why we're not quite done is that if w's are negative or positive, depending on your projection matrix, I guess that, no, we are going to make a lot of sign errors in this presentation. So the problem is if you have a triangle where two vertices are in front of the camera and one vertex is behind, if you do math on the resulting sort of screen space values, it's going to be off. So what we have to do in addition to this is we have to skip culling if vertices of a triangle are not consistently in front of the perspective projection plane. Or we can also cull triangles completely if they are completely behind the perspective plane. I don't know exactly what we're going to do yet, so for now we're just going to do, we're going to keep the W and we're going to do perspective divide. So actually the first thing we can do is we can say, okay. Does GLSL have booleans? Does this even work? Okay, cool. So I guess we only need this if, all right. All right, so the first thing we can do is we can actually say, well, if all the vertices of a triangle are in front of the projection plane, then we don't need to render it. I don't think it's a very productive test necessarily, because we do frustum culling, so we shouldn't have a lot of this geometry, but let's just see if this culling thing is even working, as in, can we reduce the number of triangles by any value? No, okay, all cool. So A, B, and C here are referring to the indices of the triangle within the meshlet. And so they have the same indexing as these data. One thing we need to do is, so if you're not familiar with how compute shaders work, then this whole thing is going to be hard for you to follow. But regardless, so all of this code runs concurrently for different invocations of sort of indices. We first concurrently transform a bunch of vertices, and then we concurrently generate a bunch of triangles. Yes, there is a loop here, but the loop steps by a very large offset. I think it's 64. Yeah, 64 right now. These values are not fully optimal, but we'll go kind of cover this in a future stream. So what this means is that before we have to think, if we want to do some work on a per vertex basis, we have to do this, make sure this work is finished for every vertex of the meshlet that we are working on, then wait for that to be true, and then actually start using this data. And so because of this, we need a barrier here. Probably if you don't place this barrier here, it occasionally works on depending on the GPU, but like it's correct to do better here. All right, so now we can just read data from these transformed vertices. So if all of the vertices are behind the projection plane, then we can call the triangle. Let's see if this does anything. Alright, it's gonna be confusing because it's V not W. 74.4, before and after. Now this might be because this thing just doesn't work at all. I would expect there to be at least some triangles like this, even though I wouldn't expect there to be a lot. Let's look at, I don't remember where we do this thing. Okay, let's see if this does anything. 440114. I don't know why it's 440114. 440114. So the stipulation is we don't have triangles like this. This is confusing. Maybe this is true. We'll have to disable realistically probably frustum culling for us to be able to tell. Let's disable near far culling and do this again. So 125, 418, 026. Right. This is surprising. This should render nothing. Wait. Yeah, the triangle count is correct. Okay. Is it really possible that, especially when we disable frustum culling, I mean, we also have occlusion culling and stuff, it would be more correct to just disable culling periods, but that's probably not a good idea. Yeah. When you disable culling completely, the system becomes, there was probably a stream glitch, because when you disable culling completely, the performance, it takes so much time to render, there's like a billion triangles. Okay, so I don't know what's the deal here. Let's just ignore this for a second. Because my... No. My expectation was that this would do something. Oh, one thing we can do... No. Let's just ignore this, because this is not the actual point of what we are doing right now. but it's a little surprising that this is not doing anything to the triangle count. Because I would expect this check to be not very efficient, as in, I wouldn't expect a whole lot of triangles to be called this way, but I would expect at least a few to be called this way. And so it doesn't intuitively make sense as to why this doesn't work. But what we need to do is the actual backface culling. So let's go back to that. So to do the actual backface culling, we need to compute the assigned area of the triangle. And the way this is done, and if the sign is either positive or negative, we need to render the triangle. Otherwise, we don't. The way you do this is essentially, it's kind of interesting that, whatever. So the way you do this is if you have the two vectors for a triangle, v1 and v2, then you can compute the assigned area. There's a thing called 2D cross product, or there was some other cool name for it, which I forgot. Perp dot, I think, maybe. But basically it's v1x times v2y minus v1y times v2x. And that gives you the assigned area of the quad, not triangle, I think. And so if you divide it by 2, you get the assigned area of the triangle. We are only interested in the side of this thing, so we don't need to, we don't even need to like subtract these. We just are interested in which one of these two is larger or smaller. So let's do that. So we need to build sort of these edge vertices, right? Edge vectors. Let's call them E, B, int vertex clip B, X, Y, A, X, Y, and then do the same for C. And then what we have, so again, we don't, let's just do this. Okay. And again, this computation is going to be invalid if some of the z's are like have inconsistent signs, but we are going to deal with this problem. Let's do this stopgap. This way, if one of the values is negative, then the boolean is going to be just set to false no matter what we do. And this is a safety thing that we kind of need so that the math above sort of holds up. All right. So EBX times ECY is either less than or greater than or whatever. Let's figure that out experimentally. EBY, ECX. So in theory, this is the backface culling test. Clearly, oh, okay, so this worked. So this is cool. When we got the sign wrong, obviously we don't see anything on screen, but we do render 60 million triangles. Why 60? So a little bit confusing, but this is because when you get the sign wrong here, you're essentially removing all triangles that you're only leaving triangles that would have contributed some pixels to the screen, which is not what you want to do. So when you get the sign correct here, we get 38 million triangles. If you remember, we started from, if we disable all culling, it was 70, it was 80 something, right? Let's do this thing again. So we're starting with 84 million triangles, give or take, and we're ending with 38. So we actually remove a little bit more than half. So it's normal, half is not like there's no guarantee that you're gonna cull half, right? Maybe the backside of your mesh is twice as interesting geometrically as the front side, and we have a lot of randomly rotated kittens, but who knows how the random numbers kind of add up and stuff like this. Like, it's normal to see the number around half, right? It doesn't have to be half. So here we are, finally something works. We are doing 38 million out of the original of 84. So that's good. Notice the test is very cheap, kind of. There's some, you'd have to look at the like assembly output for this thing on an AMD GPU and stuff like this, but we're already doing a bunch of stuff in this shader, right? We were transforming, doing quaternion rotation, etc. Compared to this, we're doing one divide per vertex, two scalar divides per vertex. And then we are doing a few subtractions and a few multiplies. It's not like a lot of work. It's not like no work at all, right? So it could be that on some GPUs, the fixed function culling units are so good that doing any extra work sort of is not productive because you can do all of this in a dedicated unit faster, given infinite area. But normally you don't have an infinite area for this fixed function unit, so like this ends up being beneficial on the balance. So that is cool. One thing, no, I think this is pretty much decent. Okay, so this is doing a backface culling plus 0 area culling for triangles. All right. I don't understand this thing. Maybe our camera is positioned in some really weird way. I don't remember anything about our camera setup. It's just surprising to see this. One way to check is, so if you only do far culling per mesh. Oh, what? What? Interesting. Maybe we just don't have any meshes behind the camera. Maybe that's what it is. Because you'd normally expect frustum culling to work. like it works, but it's not. Okay, all right, whatever. So so we are down from the original, I think we started at 75 or something, and now we're at 38.8. Now, in theory, with per triangle culling, we can remove cluster culling on a cluster cone culling, right? So the backface culling that we do in aggregate for every meshlet. But it is not productive to do this because it's very cheap test that is done at a much higher granularity. And so in aggregate, while like it's unlikely that it costs us anything. And in fact, doing this is good because it removes 10% of meshlets from the mesh shader stage before, like way earlier. And so it should probably improve the efficiency of the whole pipeline, right? We can check if this is true. So previously, before we did backface culling per triangle, whether we do cone culling or not would affect the final number of triangles that we feed into rasterizer, and so there's a lot of complicated performance implications. Now it's pretty simple. It should not matter at all from the number of triangles that we render whether we have cone culling enabled or not. So now cone culling acts specifically as an early out of sorts for the mesh shader station. So in theory, we can look at this. I wouldn't read too much into this because like there's tuning that we have to do on mesh shading pipeline for AMD. But let's just say quick test. So 10.74, if we have cone culling and and 12.04 if we don't do cone culling, but the number of triangles is the same. So we actually do get around 10% of efficiency gain on the entire system by doing cone culling, not because it removes triangles anymore, because we would have removed all of these triangles anyway, but because it removes enough work from the later stages of the pipeline that the cheap test is worth it. And this is how we should think about all of the things that we do. Does it remove enough work for a low enough price that the gains that you get from the subsequent shader stage or fixed function stage are worth the extra complexity or an extra effort on an earlier stage? Okay. So backface culling done. We need to do zero area not zero area, small primitive culling, and I also want. I kind of want to do frustum culling on a per mesh level, sorta, because just to have this be like figured out. Just to have the whole sort of pipeline work in a reasonably efficient manner. So this thing is weird. So now we could just keep this uncommented. It looks like our scene is not set up for this test to be worth it. We can just keep this uncommented. The reason why I don't love doing that is, so this test adds work. And again, there is this question, do you save enough work for the added work by this test to be worth it? It's hard to know. If in a real scene, this removes 10% of triangles, then it is possible that it's worth it because you reduce the rasterizer workload substantially. If it removes 0.01% of triangles, then it's probably not very useful. So I don't love the fact that our camera setup is like weird like this, because we can't even know. I'm also surprised, but again, I don't remember anything about our camera setup. Linear is 0.5. Like, are all of the kittens in front of the camera? How can this be possible? I think we generate them in view space, if I remember right. The R is like a sphere or like a cube. This is suspicious, honestly. Like, isn't the camera at 0 for us? Because there is no view projection, so everything is in view space. How is this possible that I don't know. Something here doesn't add up. Like, I would have expected some meshes to be behind the camera. And if the mesh is completely behind the camera, it would be called by this test. It is extremely suspicious that essentially no mesh is other mesh. The cone culling can't be that, right? We disabled. This is weird. I don't understand this. Let's leave this to do. It doesn't make sense for this to not do anything. So somewhere there must be a bug. But I can't off the top of my head figure out where. So I don't understand this. This is odd. All right. So let's move on. Let's maybe do, for a change of pace, let's maybe do frustum culling for meshlets, because it should be very easy, but it requires. So we have two things left: frustum culling for meshlets and triangle culling for small area triangles. To do small area triangle culling, we have to pass two additional values to the shader, which is the width and height of the viewport that we're rendering into. To do the frustum culling for meshlets, we have to essentially repeat the stuff that we already do in the mesh culling shader that is done per object, but do this again in the task shader. So this is frustum and Xenier. For both of these, we need extra data essentially, right? The way we funnel data to all of this right now, I think, is there's like this globals thing, yeah, which currently just has the projection matrix. Do we use globals anywhere else, by the way? Nowhere else. Okay, cool. So I don't like the word globals, so we're going to rename it to something else. And then we are going to pass both pieces of data. And then we are going to see. And then we're going to see. Yeah, so the near plane is interesting. There's a subtle difference between, but okay, yeah, let's do this. It is a little bit, it's hard. So the interesting thing about the post-projective space, the homogeneous space, is that the W that you divide by, it doesn't actually depend on the near plane. The W is 0 at the plane that intersects the camera position and is perpendicular to the camera direction. This is not the near plane. The near plane is slightly farther ahead. And so actually it is completely fine to take the triangle and do perspective division and whatnot if some of the vertices of the triangle are behind the near plane, as long as they're still in front of the perspective plane. I forget what it's called. It's maybe perspective plane, maybe projective plane, projection plane. I usually use some combination of these words. So we can push the near plane forward. We can check, right, so we can do, what we can do is we can push the near plane forward just to see if the visual, if on screen the number of triangles, like if the kitten in front of the camera is sliced in half when we do this, right? The difficulty is after we do this, it's still not clear visually where the perspective or projective plane is, because near plane is not that. But I mean, it's a good suggestion. We can do this still, right? So I don't know, let's do it 1.5. 2.5. I mean, this would explain what we are seeing. I'm just baffled. How is this all possible? Oh, okay. So 4.5 or something. Okay. 2.5. Okay. 2.5. Okay. So this guy, which is right in front of the camera, is like 3.5 units of space in front of the camera. Unfortunately, this doesn't, again, like it doesn't mean much. It is not obvious. We're rendering more triangles now after this adjustment, right? How does that work? Oh, is that why? No. What? What? Oh, is something else, is like a LOD selection dependent on this? No, it can't be, right? Some stuff is dependent on this. So, okay. Let's not dwell, like something is wrong here, right? It shouldn't, like increasing near plane shouldn't result in more triangles being rendered, because increasing the near plane does nothing to the projection component of the matrix. Like if you look at how the projection matrix works, the output W, the rest here are zeros, so it's just the input Z. Like it's not complicated. There's complicated math that depends on whether your projection matrix is infinite, etc. There's complicated math that goes around the Z output component after the post-perspective divide. But the math for W is very simple. So near plane doesn't affect this, which is why it is weird that when you increase the near plane, the number of triangles that we rasterize increases. This needs debugging. I will add this note as well, but this might be a bug someplace else, right? As in, I think 3.5. So this is something sketchy here. Like there's some bug somewhere, or I'm not thinking about this right. The fact that 2.5 was enough doesn't mean much, I guess. I don't know. Whatever. Let's ignore this. Sorry, there was something else in the chat. Yeah. So I can shift the whole thing by 3.5, and that would put the plane in the middle. The caveat is we don't actually have a view matrix right now, just because like we never needed it. I guess like we do everything right now in sort of view space, and so for this you have to. I mean, we can do this. Sure. Let's do. Essentially, you just need to shift the whole scene because like there's no camera right now, so to speak. So really what we need is, was it 3.5 or 2.5? Let's see, 3.5, okay. It's either minus or plus, you never know. All right, so clearly right now the near plane intersects the cathode. Now again, the near plane is not the projection plane, but you would think that even the projection plane right now intersects it because we are like, yeah. So we need again so if this investigation, like right now, that I want to move on from this point, but yes, this was a good suggestion. Okay, so 773405. 77345. Like, it would be unfortunate if we don't know for sure what the number that we are seeing is, because this is an output of the hardware counter. If somehow this hardware counter is like ignoring, I don't know, it's hard to. All right, so something is fishy. I don't understand this. We're not gonna debug this further. There's a number of possibilities. Like if the hardware counter somehow isn't counting triangles that are rejected in this fashion, it would be strange, but like it's possible in theory. And if this is actually true, then of course our whole like look at the triangle count on screen process is flawed because we are gathering this from the hardware counter. Let's ignore this. Let's move on to like sort of more productive stuff. I was gonna, oh yes, why am I on Linux? And there's a few reasons why I'm on Linux. One reason why I'm on Linux has nothing to do with anything that we're doing right now. So I bought a Zen 3 processor like a while back in end of 2021, I want to say, right? End of 2021, I want to say. And I had stability problems since then. Stability problems as in blue screen of death, random crashes, and random driver components. I couldn't figure out, so I didn't try swapping memory. It's pretty expensive to swap memory for like completely new memory sticks. I tried a bunch of diagnostics on memory. This didn't do anything. I tried looking, like I tried a bunch of stuff. Something seems to help, like disabling XMP in BIOS seemed to solve this. And I'm like, okay, cool. I don't care about the extra like 10% of memory performance. But then it turned out it reduced the frequency with which these issues happened, but didn't fix the issues. So I had these mirror stability problems, and I kind of at some point had enough. And the other thing is my workflow in a lot of ways on Windows is dependent on Windows subsystem for Linux. So I run like Linux inside Windows essentially. And it works fine, but there's a few things around this workflow that don't work. In WSL1, WSL2 fixes a couple of issues, but breaks a couple of workflows that I use to the point that I can't use WSL2. Perf isn't available on either really, so you can't really performance profile in a meaningful way. So at some point I just was like, let me just do an experiment. At some point something happened that turned the issue from I'm kind of tired of this to me being just aggressively unhappy. I forget what it was. So, but like at some point, I thought maybe updating to Windows 11 would solve this because I was on Windows 10 and I did this and it made things worse in some very fundamental way. I forget. Oh, right. I remember. The crashes, the stability issues broke. The crashes would often happen in an NTFS driver. I don't know why. I don't think it's related to the SSD because, like, again, no series of checks on the system as to what is wrong would do anything. So I don't have a reason to believe that the issues were with SSD. And if the issues are with SSD, I don't know why you would have a blue screen of death based on the SSD's malfunctioning. Like, this just seems weird. And also sometimes the crashes would happen in a component that's not NTFS, but it would often be NTFS. So in the end, the thing corrupted my disk, my partitions, right? So I would have like a folder that you can't open. Because I think the crash happened in a window of time where some things weren't flushed to disk, like recovery didn't work, I don't know. What I know is essentially my Windows partition was broken to the point where half of the files would randomly be absent. I had like a Visual Studio installation that I couldn't use, and I was like, oh my god, I need to reinstall the whole thing. Let me try to install Linux and see what happens. And I install Linux, and then lo and behold, zero stability issues on Linux. Zero. Now, there's the usual weird Linux problems in Linux, like audio sometimes isn't perfectly functioning or whatever, but the system works. Like, there's no, like, everything is stable. I enabled XMP, everything was stable, like, everything was functioning very well. And so I just reformatted the whole thing to Linux. I erased my Windows partition because it was broken anyway. So this was the first thing. This was the thing that actually drove me to install Linux, but right, the side effect of doing that is that you have an open source driver. This actually meant that I could explore mesh shaders very early because the version of the driver, it's just, you get it way quicker if you can build the thing from source from an open source repository. And also you can play with the driver source in interesting ways, which maybe at some point we'll explore more. But yeah, so the reason for me going to Linux had nothing really to do with Vulkan, but it had this nice side effect of I now have open source drivers and stuff like this. Not just we are using RADV, not AMD VLK, so I have AMD VLK set up now as the main driver. I did this like a few days ago. It doesn't actually have full mesh shader support yet, but that thing isn't built from source. The nice thing about RADV is building Mesa from source is really a nice process. You install a few weird dependencies, which is not nice, but then you build the whole thing and it builds from scratch in like a couple minutes. I forget what it is. Incremental builds are very fast. It's you don't have to build the LLVM. Like, it's a very nice process. It feels from the instruction page on AMD VLK, it felt like that build process is much more complicated. So I didn't really want to brave that. But like, we could. Even that is open source, so there is a possibility of building it from source and playing it, like changing the source and seeing how it affects things. It's just I didn't do that because the code base feels more difficult to work with. Anyway, all right, so this was a digression. Yeah, debugger story is maybe not ideal. I use GDB anyway a fair bit on Windows because of my setup. But yeah, I kind of have to use GDB these days on Linux. Unfortunately, it's not great. It's not there. I'm used to this. It's not good. I'm just used to this. All right, so digression over. So let's ignore the weird stuff that seems to be happening with our like camera thing. We'll have to look. It's a problem that I don't know what is going on, but we are not going to fix that problem right now. We are going to do other stuff. Okay, so I want to rename globals to render data or something like this, because I don't like, both names are terrible, but we are going to maybe I already regret this. All right, let's not do this. I thought I would rename it to a nicer name that doesn't imply, like, it's a struct that is passed to the through rendering geometry as a push constant buffer. Like, it's not global in any meaningful way, but I realized I hate the name render data as well, so let's actually not do this. The real thing I wanted to do is I wanted to put the data that is important for culling, for more culling, into that struct. Now, what? So there is, and this is going to change a little bit, but there is a size restriction on the push constants. We're currently using push constants in a sort of loose, like not fully optimal or recommended manner, but we have so few draw calls that really none of this matters. The size, I think the minimum size limit for the push constants, like the number of bytes that you're guaranteed to be able to use with push constants, is I think 128. A 4x4 matrix is 64, so we do have space. After we put in 32 bytes, we are close to being out of space, but we do have space. So let's put this data there. Let's fill it on the CPU side somewhere. So essentially we need this, right? Okay, and I actually don't need, what will we need? So we'll need frustum planes, left, right, top, bottom, and near, far, to be able to do frustum culling for the meshlets, which is what I want to do, just to get it out of the way. I don't think it's going to be, so this is for the case where the mesh fits in the frustum, but parts of the mesh are off screen. I want to do this just to see how well this works, and if we do this and it saves us something, we'll probably not have to worry about this on a per triangle level. For this, you need frustum planes and you need near far. I don't think you need these guys, and these guys are kind of redundant. Like projection matrix, these are two elements of projection matrix. Near, I think, is in the projection matrix. Far, I think we use an infinite projection, so for us the far plane is an artificial construct that just limits how far we draw. It doesn't limit the actual projection parameter. So realistically, we could have just, like, for example, we can remove the projection matrix from here and do the projection math ourselves, because if you look back at the projection setup, which we just had somewhere, this guy, so most of this is zeros. This is not zero, this is P00, this is P11, and then there's the near. So technically, it's fully expressible by P00, P11 is the near. Technically, we don't really need it. And it actually could be beneficial for us to remove it, because multiplying by a projection matrix is like more work than, if you know that most of the elements of your matrix is zero, you can more efficiently multiply it by it. But we can replace this in the future with a view projection matrix, so this is less of a big deal. The thing I want, though, is I want screen width instead of this and screen height, because this is going to be important when we are doing pixel culling for triangles. So that's just add this here just so that it's there. And then and screen is a bad name. Everything is a bad name here. Don't use my device for naming things, I guess. So I don't know where. Swap chain.width and swap chain.height. Okay. Okay. I think this is probably everything that we will need. Right, and then we are still repeating all of this, which at some point we should have fixed, but whatever. Okay, so getting back to this. So now we have some data in that should be in our mesh shader, and the way we work with push constants right now is that we use the same push constants in all of the stages, which means that it's very easy for us to just, like, we don't have to think about, oh, do we need this in mesh shader, do we need this in task shader, etc. It's not the most efficient way to work with this, but again, for a few draw calls, it really doesn't matter, I don't think. It mostly doesn't matter. It matters a little bit, but mostly not, I would say. And on AMD hardware, the real reasonable number of push constant data, amount of push constant data that you can push directly is on the order of like 1632 bytes. So realistically, even before we added this stuff to globals, the driver would have used an indirection to read the push constant data, and at this point it doesn't matter what you add. So it's fine. Now, what we can do is we can use this to do frustum culling. And we are going to attempt to copy this from our other shader. And just do the same thing. It's actually where, so actually I don't know how much, so we do all of this work, I guess it doesn't matter. We do all of this work on a per mesh basis, right? So this is an attempt to say, hey, if we do this on a per meshlet basis, do we call more triangles almost for free? Because all of the math that we do here, it's pretty cheap. If an average size of the meshlet is like 90 triangles or whatever, then there's almost 100-to-1 ratio between the rate of execution of math that happens here versus rate of execution of math that happens in your mesh shaders. There's also, if you have 100 triangles per meshlet and 100 meshlets, that's 10,000 triangles, which is on the higher side. But if there's probably between 10 to 100x ratio of realistically of meshlets to meshes. And so these stages that we were talking about, the meshes, meshlets, and triangles, there is between 10 and 100x of reduction or inflation of numbers between these. And so whenever you can push something up in that sort of chain without losing too much efficiency, it's good because you're dramatically reducing the effort required in doing that, in doing that computation. So let's just attempt to, I'll have to, if this, I don't know if this is correct, but we have the center and the radius of the meshlet. It is in the same space because everything is in view space. We have the radius, it is all scaled. we already had to compute all of this stuff. Like, this might just work. I don't know. Let's see. Okay. This worked. 30, was there 38.1 or something? Let's do this again. 38.8. So this is good. So once we do this, we are down to 37.1 from 38.8. So it's a small reduction. It's a reduction of 1.7 million, which is what, 5%-ish? But it's good because the cost of doing this reduction is probably very small. We can look at the total GPU time, which might not have changed a whole lot. 1027. Was it similar? It changed a little bit. So we went down from 1075 to 1027. So this is a small thing. It is nice to do because, see, again, a lot of this stuff is once you do some amount of work here, you have to compute a bunch of stuff. So here we had to transform the mesh bounding sphere to the view space because we needed that to be able to do culling correctly. Once you have this data, so this is the code that we used to have, right, before this addition. Now that you have this data, this is like a few scalar ops to add. And so adding a few scalar ops per meshlet for the purpose of getting the extra, 5% I said reduction in the rasterized number of triangles, it's really good because you're reducing the amount of work on mesh shaders, you're reducing the amount of work on rasterizer for relatively little work in the task shader. So this is cool. If you're confused as to what all of the task shader terminologies, etc., you'll have to refer back to whenever we did mesh shaders. I'm not going over this again here. Okay, so this is awesome. This works. We don't know if it works, but our scene, the good way to tell if the culling algorithm is correct is if you switch between the mesh shader path. Oh, this is actually interesting. This does not fully work. Why doesn't it fully work? Oh, this is cool. This is because our far plane, right? So, in general, when you switch between the mesh shader path and the fixed function path, you should not see anything changing, because you're trying to do the correct thing, which is to cull things that wouldn't have been visible otherwise. I don't know if you can see this on the screen or not, but when I toggle, I'm pressing the button that switches between mesh shaders and not mesh shaders. I don't know if you can see this. There is a few pieces of geometry that actually disappear. I suspect that if I remove the far plane test, then this fixes itself. Yes. Now, we are in this position where the Z far that we have is artificial. As I said, the projection matrix that we're using is infinite. It results in better depth, precision, etc. But one consequence of this is that it doesn't matter how far an object is from the camera, as long as it's in the frustum, in the infinite frustum, you can render it, and it might result in like a couple of pixels on screen. This is difficult to work with from the performance perspective. You can't realistically render infinitely far away. And so we have this extra artificial thing, which we call Z-far, but it's really draw distance, which is how far do we render stuff. Now, right now, before this change, if the mesh is entirely outside of the Z-far, we wouldn't render it. But if it's even partially inside the thing, we would still render the whole thing. With this change, if a meshlet, if part of the mesh is behind, we would not render it. So this explains why there's a difference. I'm still gonna keep this, I think, because why not? It's not a huge deal. Like, we could remove this. Let's add a note. This may call. We could optionally. So I'm not going to do this right now, but if you wanted to adjust this in a way that is exactly the same between the two pipelines, you could kill that. It's probably not, let's see how many triangles that thing alone is, 37.1. 37.5. It's an appreciable number. It's 400k out of 38 out of the delta of 1.7. So it's like 25% of the gain is just the departure. We can remove it. If we wanted to be conservative, I'm gonna keep it for now because like on some level it seems fine to keep it. The concept of having this far plane is a little bit questionable to begin with because the mesh is going to essentially disappear at some point while it's still sort of visible on screen, right? But you can't, again, realistically render infinitely far away. So it's a practical efficiency thing. All right. So this is good. We're done with 2 out of 3 things. We saved the gnarliest for last. It's not the gnarliest because it's conceptually very difficult to do, but it's kind of the gnarliest. So if you look again at where we are at right now, so we do frustum culling on a per meshlet basis, which probably is reasonably close to, we can try to do this on a per triangle basis, and it's gonna cull a few more triangles. Let's see how difficult it is to do, because maybe we'll just do that. We use this weird symmetric formulation with radius, which doesn't really work very well for triangles, so we'll have to change some stuff to be able to run the same code on the per triangle level. Now we don't have to use this formulation because we can just, but if you call individual 3 vertices, it doesn't. I don't want to do this on the triangle level. It's a little, there's like caveats. You have to call all 3. We can do this. I just don't want to. Why is center.z? Right, so this does simultaneously plus and minus center.x. And then what we have to do, so what we'd have to do is we'd have to test 3 vertices of a triangle against individually left plane, right plane, top plane, bottom plane, etc. And for each one, yeah. So I suspect it's not super necessary now that we do meshlet based culling, but it could remove some number of triangles. And again, there is this complex question that is hard to answer in general. Is it worth it to spend X extra UOPS to have small amount of reduction, right? The reason why we did this in the meshlet is if we don't do this at all, then it feels more worthwhile to do this on the per triangle level. Once you do this on a higher stage that's like between the meshes and triangles, then you reduce the need to do this on the per triangle level. But the whole thing is about efficiency. The reason why you have to do this on this GPU, the reason why you have to do backface culling on this GPU realistically is because just doing this on the meshlet level is like 10% reduction in triangle count, and doing this on the triangle is 50%. It's like a huge difference, right? If doing this on the meshlet level was 95% of efficiency of doing this on triangle level, then the need to do this on the per triangle level is much more questionable. All right. So now the problem that we have is, so we end up with 37 million, which is better than the number we started from, which was 75, I want to say. But in the traditional rasterization pipeline with drivers doing the magic, it's 6.7. So we're still like 6x, 5x off from whatever the driver is doing. The reason for this is that the driver is doing frustum culling on a per triangle level, but this might not be that impactful. The more important reason is that it's doing small primitive culling. So what is small primitive culling? It's tempting to say if the triangle is very small, it doesn't have to be rendered. This is not quite the case. So if you have a pixel grid, and these are the centers of pixels, If you have a triangle, where are the colors here? Hello, where are the colors? Oh, hold on. I'm looking for how to change. I'm confused. Where is the color select? Oh, here's the colors. Okay. So the red triangle is not rasterized. It is dropped by the rasterizer, or rather it results in 0 rasterized pixels. The reason for this is that the rasterization rules say that the triangle has to cover a pixel center to rasterize that pixel. This one doesn't. However, you can have a very small triangle, a very tiny triangle, that just covers a pixel center. So a rasterizer does rasterize the green triangle. It does not rasterize the red triangle. From this perspective, what we can do is we can try to distinguish the red from the green, right? But it's not purely a size check. It doesn't say, oh, the triangle is too small, so we don't rasterize it. In fact, if we try to do this, what we'll end up with is pixel size patches, like holes inside the thing that we are rendering. And in fact, we can try to do this, but this is what will happen if we try to. The correct thing to do is to ask the question, does a triangle intersect any pixels? Now, the question can be difficult to answer exactly. For example, let me draw another triangle. So I'm gonna do my best. It's hard. Okay, hold on. So something like this. This triangle is interesting because it doesn't intersect any pixel centers. However, if you adjust it even a little bit, it will start to intersect the bottom left pixel in this 2x2 pixel grid, right? And the triangle is pretty tall. Like the green triangle is smaller than the pixel on every dimension. The blue triangle is actually larger than the pixel in the y dimension. Despite that, it doesn't result in any pixel. So this is difficult to do precisely. But again, we don't need to do this precisely. What we need to do is we need to identify triangles that are definitely not intersecting pixel centers and have a reasonable degree of confidence, like cover a reasonable number of triangles that in practice don't intersect pixels with a test like this for it to be worth it, right? So the usual thing to do in cases like this, the usual approximation for things like for something like this is this. First, go from the triangle to the bounding box of the triangle. So instead of asking, it's basically the entire simplification. So instead of asking if the triangle covers any pixel centers, we will draw a bounding box around the triangle and ask if the bounding box covers any pixel centers. In cases that I draw here, I won't draw this, but like you can imagine the bounding box, the axis-aligned bounding box around the blue triangle will cover both centers, and the axis-aligned bounding box around the red triangle will not cover any centers. How do you check? So let's say we do a bounding box. What do you do after this? What you have to do is you have to ask essentially, if you look at this from just one dimension, like if you just look at the x, what you have to do this bounding box test is you have to round the, let's do this for the red thing, for the red triangle. So let's look at this, let's look at the projection of the red triangle along the x-axis. So it's a line that goes like this. And then there is 2 pixel centers, here and here. So what you have to do is you have to round the coordinates of the endpoints of this line in the same direction, for example, down, to the nearest pixel center. and then ask, are the results the same or not? For example, here, if you round these guys down, then you will round the low endpoint to the red dot and the high endpoint also to the red dot. And if the results are the same, then the whole thing is sort of in between two endpoints. Now, the caveat is that this simplified exposition that I've done here ignores triangles that are that start exactly on the pixel border, and also it ignores a thing called subpixel rasterization or subpixel snapping, or I forget what it's called. So there's some imprecision in all of this. We are gonna skirt by the imprecision by basically adding like epsilons to a couple things to make it all work out. I don't promise that the code that we are going to write right now is like strictly guaranteed to be accurate for the rasterization rules that are guaranteed by whatever standard we are using. But you can figure out, it's just a matter of tweaking something slightly to fit the specific thresholds on the rasterization that you have. So like the code that we'll write might not be precise, but it is within a small distance of precise. The other thing to note is that if you use multi-sample anti-aliasing, things become complicated because you're asking the question, you're not asking the question, does the triangle intersect the center of the pixel? You're asking, does the triangle intersect any of the centers of the samples? Which is hard because a 4x4 MSA grid may actually have the centers like here. It's like a weird rotated grid by default, like this. This is good for MSA because it reduces stair stepping and stuff like this, but it's bad for triangle culling because like, how do you efficiently, like you can't do these approximations anymore. You have to more explicitly ask, does the box intersect the centers? You can still do this. You can also change the locations of the samples in MSA if you use Vulkan or DX12. You can also ignore the problem because we don't use MSA. So we will ignore the problem because we don't use MSA, but MSA throws the range into this like simplified procedure. Oh, oops. I don't know what I pressed. Okay, I pressed F5. All right, so this is the idea. It almost takes. We'll have to. The code we will write right now will probably not work from the get-go, but the code shouldn't be too difficult to write. It's like it takes almost more time to like explain the process than to actually implement the code. Oh, and I should mention this is relatively standard stuff. I think Graham's presentation has a section on this that goes maybe in more detail, maybe it doesn't. Let's see. So it talks about MSA. Oh, this is not culling yet. It uses the same colors for triangles, more or less, that we've done. This is a similar example to what I was drawing. Yeah, in this case, like a triangle is more than 2 pixels tall. Oh, it says you should round to nearest instead of... I mean, it's a matter of a half offset, sure. We can do round, it's fine. These things get nuanced on like in edge conditions. So again, like rigorously, when you do it rigorously, you have to evaluate this a little bit. Like you have to do the math a little bit more carefully than I'm doing right now on stream, but it doesn't talk about this problem. Everything, which is annoying. So is the stream actually back? As to what the YouTube is telling me, because it's saying 2:30 What does this mean? Oh, like it cut half of the, I think it shifted the timeline, right? It probably shifted the timeline. All right, so I don't actually know what state we are in right now. Right, so this is me. So, okay, so this says the stream is back, but the middle half an hour of the stream was effectively cut away. Okay, so this sucks. I'm sorry about this. OBS crashed. OBS crashed and I didn't notice because when OBS crashed, it didn't display any like notifications or anything. It just crashed. And I was writing code. So this is unfortunate because we ended up writing the code that worked. And I talked a little bit about the conclusions. Let me repeat the summary because I won't go over, like, we won't write the code that we've already written again. I think the stream cut off at a point roughly when we just finished talking about math implications of small primitive calling. In the half an hour that the stream has been gone, well, I thought it is recording, we ended up implementing small primitive calling. It took a few lines of code. I talked about complications with subpixel precision, which is where the naive model of, here's a triangle, let's put a bounding box around the triangle and quantize it to like individual pixels and stuff, doesn't fully work on real GPUs because they do the sequence of operations in slightly different precision than sort of 32-bit floating point and stuff like that. So there's a little bit of fudge factor that you have to apply, and there's sort of principled way to do this and less principled way to do this. We went for less principled way to sort of get it to work. What we ended up with is working subpixel calling, and it got us down to 6.8 million triangles. Whereas the traditional pipeline with the driver doing whatever it does is generating 6.7, which is good, as in we are close enough. We have two big problems that we have not fully resolved, which we will resolve in the future. So let's do the recap. So I'm sorry about the, thank you for notifying that, you can see this again. We wrote some code, the code works, this is good. It's unfortunate that we lost the process of writing the code, but because of this, we did end up, this is really the code that we've been writing for half an hour, but with like explanations and stuff. So if you disable this, then we render 37.5 million triangles. If you enable this, we render 6.8 and or rasterize 6.8. And there's not an appreciable difference between them. Like you can toggle the thing back and forth. It seems like it's the same picture. And the reason is we are carefully, hopefully, sort of rejecting triangles that the rasterizer wouldn't have seen anyway because they don't intersect pixel centers. Now, we have, so because of this, we essentially went from the old pipeline that we had to the pipeline where on a triangle basis, we call by orientation, so backface calling, and by size, so small primitive calling. On the meshlet level, we added frustum calling in hopes that we wouldn't have to do frustum calling on a triangle basis, which is probably true because as you can see, I believe the driver does do frustum calling on a per triangle basis, and there is small inefficiencies in some of our calling stages, but they add up to 6.8 million triangles rendered versus the driver's 6.7. So we are like reasonably close to being reasonably good. This is probably what this extra 0.1 million could come from two places really. One is we are doing small primitive calling too loosely. And in fact, this is true. There's easy ways to change the code that we do to produce fewer triangles. I just am not very confident in the math with flipping and stuff going on that I don't want to I don't want to commit the code that I feel is probably buggy, and it's hard for us to do a perfect test because it requires a more rigorous testing framework, which we don't have. But so we are within reasonable proximity. We are doing slightly loose small primitive culling, and we also don't do frustum culling on the per triangle level, which might lose us some. But overall, we are close enough to what is probably perfect on this scene. We don't do per triangle occlusion culling, right? But I think it's not really reasonable to do this per triangle when you have mesh shaders. You should do it on a per meshlet basis. So realistically, the pipeline that we have from the culling perspective can be improved by adding occlusion culling for meshlets, which is number 2 here, which we might do at some point in the future. But other than this, we are solid here. The thing that is not solid is the fact that on an AMD GPU, we are way better than we were when we started the stream. We can check how much. So when we started, it took us 16 milliseconds to render whatever we are rendering right now. Now it takes us 10.5. So it's a substantial improvement, but the driver without mesh shaders or without explicit mesh shaders is still doing a better job at performance, even if the triangle count is very similar than we are, because the driver takes like 7 milliseconds or something, 6.5, it's hard to see. So we are still slower than optimal. This is because of inefficiencies in how we are configuring the mesh shading pipeline, coupled with the fact that the hardware, AMD hardware, doesn't actually support mesh shaders. It supports a slightly different construct. And when you map from mesh shader workflow to that construct, you have to take trade-offs that are different from the trade-offs that we've taken so far, right? So like stuff needs to change for us to actually get to the peak hardware efficiency, which we are not going to be doing right now. So that is kind of it for the stream. If it didn't go down for half an hour, I would have said that it went really well. Instead, it just went okay. Unfortunately, on YouTube, because OBS crashed, this is whatever you saw is going to be what you will see on YouTube, with presumably half an hour of just the stream being dead, like cut. But I will publish the link to all of this on Mastodon, and I will commit the code that we have written to the repository. We've done this on AMD. The code should work on an NVIDIA chip and on Intel chip if the Intel driver implements mesh shaders by now. I don't have an NVIDIA GPU to test this, so I don't know. It is very easy for anybody watching to try to get this to run on an NVIDIA hardware and, for example, check if adding or like basically changing whether culling of triangles is enabled or not in the mesh shader, whether this affects the performance at all. And I should also say that on the NVIDIA hardware, we might be running, when I did the mesh shading port from between 2 different extensions, I had to change this thing. Can I change it back now? I can. Oh, well. No, hold on. Oh, this is the MD thing. So there's weird. Ugh. Hold on. Let me. I don't want to commit this. I won't commit this. There should be a to-do here, really. So this node is not very interesting, actually. But I should write a to-do here. So there's problems with portability of mesh shaders between NVIDIA and AMD, and maybe Intel. I don't have an Intel GPU to test. From the performance perspective. So like the code that we've written should work on NVIDIA, should be fine, but we have performance issues on AMD, and some of the earlier changes that I had to do to make AMD work a little better probably made NVIDIA work a little worse. So this requires rethinking in terms of what exact code we have in this shader. which we are not going to do right now, but I just wanted to note that you should be able to run this code on NVIDIA after all of these changes. Is the code perfectly efficient on NVIDIA after all the changes that we've made? I'm not sure. It depends. It's a subject of another kind of exploration. All right. So with that, let me commit all of this. So let's just call this day 7. 7 enhance mesh set and triangle culling. We now implement frustum culling of individual meshlets and backface plus small triangle culling, small primitive culling for individual triangles in mesh shader. The former is unambiguously good, really, unambiguously good. The latter may or may not be worthwhile, depending on a complex set of sort of microarchitectural hardware really conditions and let mesh shader setup, which we do not do optimally at this time. The summary of this essentially is this. Like right now, we are slower than the non-mesh shader path on AMD hardware, even after the changes that we've done. It should be possible to be faster or at least the same speed. Like there is no reason why it's fundamentally impossible to get to the same level of performance, I think. Probably. It's complicated. There is a small reason for why it might be. It's hard to know, but it's probably possible. However, we are not there yet. It requires a bunch of changes, and once we do this, it's not clear if the new thing works well on NVIDIA or not. So let's push this, and then so when I was talking about the rigorous testing framework, and I mentioned this while the stream was down, but essentially briefly, so this code that we've written like to call, yeah. So I was talking about this while the stream was down, where there's this subpixel precision thing which reduces the internal rasterization precision in certain stages, which affects whether the rasterizer considers a given triangle to intersect or non-intersect the pixel center, which is really the approximation, which is really the test that we are trying to approximate here. Now, we have some code that I've written that on this GPU seems to work. But when I say seems to work, it means I toggle between this code being on and off, and I don't see visually differences. Realistically, something like this to actually guarantee correctness, not guarantee, but to have more confidence in this code really should A, be run on multiple different vendors. B, instead of taking a fixed camera position, you should vary the camera position and validate that the frame with this code versus without this code is exactly identical by taking the screenshots and comparing them. They should be bitwise identical, right? If they're not bitwise identical, there's a bug in this specific code. They don't have to be bitwise identical between two different vendors, but within a single vendor, having this code enabled or disabled should have zero effect on the output picture. And we don't have like code to actually grab these images and diff them and whatever, right? So this is what I meant. If you wanted to have this code be provably correct, like not like, oh, hand wavy correct, or not like, oh, we tested it on a few cameras on a few vendors and they produce the same result, but more like any GPU that conforms to the Vulkan specification must produce the same results, then it's more difficult because one, we are hard coding the subpixel precision bits, which conforms to Direct3D 11 spec, but the Vulkan spec is much more loose. So in theory, it's possible to produce a GPU that breaks this very trivially. B, you have to do floating, you have to look at the spec and what spec guarantees and doesn't guarantee and do more precise floating point analysis. Like it's hard to actually prove that this is rigorously correct, but it's possible. It's just much harder. And I will not attempt to do this on stream. the situation around the mesh shaders in general is complicated. Let me spend a little bit of time talking about this so that we try to compensate for the stream being down. So the state of this code right now, right? So the state of this code back when we were developing this like several years ago on NVIDIA hardware has been that mesh shaders resulted in higher efficiency of rasterization compared to traditional rasterization pipeline on NVIDIA. This was on 20 series NVIDIA GPUs. So since then we had 2 generations of NVIDIA GPUs. Who knows whether they have changed anything. This was before triangle culling and stuff like this. This was with the NVIDIA specific extension, not the Chronos extension, because it didn't exist at the time. And I haven't checked what things look like now. And as I was saying, we had to change some configuration and stuff to like make things probably less efficient on NVIDIA. It's all fixable, like we can go back. It's just difficult since I didn't have an NVIDIA GPU when I was porting this. It was hard to say, oh, my change is neutral on NVIDIA, because like I don't have an NVIDIA GPU test. So on an AMD GPU, things are weird. On an NVIDIA GPU, there is NVIDIA doesn't publish hardware details, so who knows? But they have made the original extension. My understanding is the NVIDIA GPU internals are not too far removed from the mesh shader model. Like it's not crazy match. On the AMD GPU, the match is a little bit crazy. And it's a little bit crazy in very unfortunate ways, as in the driver has to do a transformation on the mesh shader to the actual shader transmit hardware, which is called the primitive shader. This transformation is not just mechanical, it is a little bit, it's mechanical as in there is an algorithm that does this, but it changes some things in like in ways that break the computational, not the computational, but sort of the efficiency model of the mesh shader to begin with. I don't want to go into too many details because it requires more time, and I roughly understand how all of this works on the AMD hardware, but what I haven't looked at yet is, so when you use vertex shaders, they do use the same unit now. The driver uses the same unit that the mesh shaders use to do the triangle culling. This is why on AMD driver, unless you disable that path in the driver explicitly, you end up with very few triangles, with much fewer triangles rasterized in our scene than you are kind of feeding the system, right? But they do it efficiently. And so like there's a little bit of a difference between what the driver does when vertex shaders are enabled and what we can do with mesh shader extension. It's a little difficult to explain and stuff like this, and so like it requires a separate stream when we talk about this and try to attack this problem and stuff like that, right? So the upshot of this is on NVIDIA, even if our code base has been made worse by whatever changes I have done without having an NVIDIA GPU, I feel pretty confident that we can get back to being efficient or as efficient or more efficient or whatever than traditional pipeline. On AMD, it's a whole separate story. It's probably possible to be more efficient, but it is difficult, especially since the driver does the culling now for you. If the driver didn't do the culling, right, so when we talked about mesh shaders, the argument was initially, like several years ago, the argument was, well, we can feed less data to the fixed function unit and by doing culling. Well, if the driver does culling for you, with code that is optimized for the given architecture, etc., now it's like, how do you write portable code that actually beats the driver, right? So on AMD, things are complicated. Intel, I don't know anything about. It requires a GPU to test. It requires to play with a bunch of variables. It requires looking at, I don't know if Intel ever published the documentation about how their implementation of mesh shaders sort of works, right? So I don't know. All of this says today, I'm not, I feel like there's some evolution in hardware that has to happen for mesh shaders to be an obvious choice. They are still a good option for you to rasterize stuff with when you know what the hardware implementation is and your algorithm maps well to this. It's just different between NVIDIA and AMD substantially. It might still be a good option if we've tried to use mesh shaders to render regular geometry more efficiently, right? There is a world in which you're trying to generate geometry. In that world, your alternative is geometry shaders, which are very unlikely to be optimal, more optimal than the mesh shading. So but it's hard, right? So it's hard to know on this task that maps well to the traditional pipeline. Can you beat the hardware at its own game? I think so far the answer for NVIDIA has been yes, and the answer for AMD so far for our code base is no. It's not because it's impossible, it's because there is configuration issues and stuff. But once we fix these issues, I don't know if we are going to beat the traditional pipeline. I haven't tried that yet, right? There will be a separate stream where we try to explore this. So overall, I don't know yet where mesh shaders lie, right? And the other confounding factor is mesh shaders today they have graduated. When we started the project, they were an NVIDIA-only feature. Now they have graduated to be a desktop feature, as in they are supported by DX12, there's a Vulkan extension that is cross-vendor. On Linux, I believe there is 3 implementations of this extension for 3 vendors, right? So it's all good. And Apple supports mesh shaders on Metal. So that's all good as well. But there hasn't been any use for mobile. And so to what extent mesh shaders are a truly cross-platform technique as well for generating new geometry, not just rendering an existing sort of static scene, I don't know. So I don't know. I can't confidently say one way or the other, oh, mesh shaders are the future of rasterization, or, oh, this was a terrible idea. The fact that there is a vendor, AMD, which has a substantially different hardware isn't by itself indicative yet of sort of... AMD had primitive shaders before NVIDIA shipped an extension. They just weren't... The use case was always triangle culling. The use case wasn't like anything else from what I understand. And this is why it feels like the trade-offs in hardware have been made the way they have been, right? Like, can AMD change the hardware to map better towards mesh shader model? Probably. Like, I don't see a reason why not. Will they do this? I have no idea. Is it a good idea? I don't know, right? I'm not a hardware designer. So I don't know. It's hard to know. It's hard for me to know sort of where mesh shaders lie today in the whole spectrum of like what you could be doing. When they shipped, it felt like, oh, this is a clearly superior alternative to geometry shaders, and it succeeds at the areas where geometry shaders fail. I don't want to make the same statement today, but I also don't want to make the statement that mesh shaders were a failure. Like, it's not clear. More time needs to have more, so there is more experimentation needed on my side, at least, to be able to get sort of to be able to be faster on AMD versus, for example, not using them to begin with, and then to answer the portability questions. Intel is a sort of uncertain variable in the mix. I don't know what the hardware is and how it works. And just in general, it's a space that needs more work, more research. I haven't tried to implement tessellation in with mesh shading pipeline, but it should be possible. It's gnarly. Tessellation is difficult to do. Like, the tessellation algorithm is not very fun to work with. So I don't know what the efficiency considerations are, but like, you can do this. I don't know if there are existing implementations yet. I think the hope for mesh shaders has been that it's the only hardware portable sort of amplification / geometry programmability pipeline. And then everything else that we have today, geometry shaders, tessellation, whatever, is compiled to that by the driver. We aren't seeing that yet. I don't know if we will ever see that. It's hard to know, right? it would be very fun to see NVIDIA publish Kronos, not like a Vulkan layer, an open source Vulkan layer that does the translation. Like it would be interesting to move some of this stuff with tessellation and geometry instead of away from the driver, but it probably compromises efficiency in certain cases, definitely on AMD. So I don't know. Well, I shouldn't say definitely on AMD. AMD is an interesting. I don't fully understand AMD's geometry pipeline to be able to comment on that in earnest. So I don't know. But yeah, I haven't implemented tessellation myself. It should be possible. I haven't seen people do this, so I don't know if there's an existing implementation. All right, so let's end the stream because we've talked about everything I wanted to talk about. We lost the segment, unfortunately, but everything else was there. And the code is already pushed, I think, to GitHub. So if you want to test this code on an NVIDIA GPU or whatever, be my guest. I don't know if there's going to be... I know what the next stream would be about. It would be about these like hardware efficiency questions that we've explored. I don't know when it would be. It would not be this year, I don't think. It's very unlikely that it will be this year, let's put it this way. Let's just say it will definitely not be this year. But when it would happen next year, I don't know. Maybe we'll try to do it in January sometime. And next time I will be aware of the fact that OBS on Linux may crash in the middle of the stream, and we'll try to watch for it. All right, thank you everyone for tuning in. The recording will be on YouTube and the link will be on Mastodon or whatever. And till next time.